Well, thank you, everybody. My name is Chris Gabrielli. I am a project manager at SelkerMetrics, and today I'll be discussing a little bit about sediment movement and looking at scouring and deposition through continuous measurements over large areas with DTS. So our primary work at SelkerMetrics is actually generally focused around locating groundwater seeps. We do most of our work at large Superfund sites and big industrial waterways. And we initially would do our installations by just laying a fiber optic cable on the sediment surface, but we found pretty quickly that the temperature signal that we received from this was often quite messy. And so it was often difficult to discern the difference between, say, just a cold, deeper section of installation site in the river from an actual cold discharging groundwater seep location. And this ultimately led to us to bury our fiber optic cable. And initially we would do this by through a scuba diver, which was fairly laborious, but we moved quickly into plowing the fiber optic cable in with a plowing device. And this is just a prototype of a plow here in the picture. And this really cleaned up our temperature signal. With this, though, we also wanted to be able to measure our the discharge rates of these groundwater seeps. And I should actually mention that ultimately the sedimentation monitoring that we've been doing is really just a byproduct of this groundwater seep work that we do. So I'll discuss a little bit, as I'm doing now, of this groundwater seep location and quantification, and how that's ultimately led us to this new method of being able to monitor scouring and deposition. So in order for us to basically identify or quantify seep discharge rates, understanding or knowing the burial depth of the fiber optic cable is fairly critical in this process. But these installations produce very variable burial depths. In theory, the plow buries the fiber optic to about 10 centimeters. But the reality is that the sediments are often very variable. They go from soft silts, which are easy to plow in, to much harder, more armored gravels. And then in the industrial waterways, we often run into sunken cars or shopping carts, logs, stumps, you kind of name it. So we have a very varied burial depth, which we need to basically get a better sense of. And fortunately, the temperature data that we're observing in the fiber optic cable can actually reveal the burial depth of the fiber itself. And we do this through a very simple matching algorithm where we match the observed temperature with a modeled sediment temperature. And so temperature changes in the surface water propagate through depth into the sediment, and they vary by depth into the sediment. And we basically just match our observed fiber optic cable temperature with these modeled sediment temperature. So this is just an example of sort of one spot in the fiber optic cable, and we are trying to understand how deeply is it buried. So we use a one-dimensional finite difference heat transfer model, and we feed that with surface water temperatures, and it basically just models the sediment profile temperatures to depth. We go to about 1 meter, and we model it at about 2.5 to 5 centimeter depth increments. And we just basically then match our observed fiber temperature at a location to these to the modeled sediment temperature. And then from that, it creates a very easy approach to back out the burial depth. And this is then highly scalable. So if we can do it at a single location, we can basically do it at all of the locations along a fiber. This is an example of a installation at an East Coast river system where we put in just over 6,000 meters of cable. It covers about 20 acres or so, and we have half-meter cable resolution here, or fiber temperature resolution. And so if we can do it at one location, it scales up easily to the entire fiber. This is cable burial depth across the entire fiber. And we go, for this one, we're moving from unburied cable, where you see the blue, to greater than 15 centimeters of depth by 2.5 centimeter increments for this one. And again, this is scalable quite easily from a single point in time to integrated over multiple time steps. And I'll show you a 21-day integrated animation here of sediment movement through time. We've interpolated this so it creates a nice, smooth, planar surface. And we can basically get a sense of sediment movement at a daily to sub-daily time scale. I'll play this last little bit again because it's a little bit more active with this approach. And right now we're actually working with a group at OSU in their in their wave lab to refine this approach, get a better sense of sort of the critical boundary conditions, some of the sort of the uncertainties and errors associated with it, and just to validate the results a little bit more. But overall, we can get centimeter scale depth accuracies with our cable burials. And so that gives us about centimeter scale depth accuracies for the sediment movements. We can get temporal resolutions daily to sub-daily, and this is very much controlled by the variability in surface water temperature changes and how we can model them to depth. And then our spatial coverage basically is similar to the spatial coverage of our overall installations, which is single to tens of hectares and up to many kilometers in length. And so we're pretty excited that the single fiber optic installations can give us seep identification, seep quantification of seep rates, and then also observes the scouring and deposition all in sort of a single go. And if anyone would like more information, they can reach out to Frank Selker, our principal, to discuss this further. I think I probably flew through that, giving us plenty of time. Yeah.
Awesome. Thanks, Chris. There are definitely some questions. People are wondering, how did you get that cable so straight in the water and keep your GPS all squared away?
Yeah, so we've played with a lot of different installation approaches. We basically will anchor the cable at one location and then motor with a boat to the other end of the transect. We'll drop spuds or anchor the boat in some manner at that other end, and then while we're motoring, we're both spooling out the cable and spooling out a rope that's tied to that to the plow system. And then from the far end of the cable, we'll use a winch system, and we'll winch the plow with the rope over and on top of the fiber. And the plow basically feeds the fiber through the plow system, through a trough that the plow is buried, and then covers the fiber up afterwards. And then when the plow reaches to us, we lift it out of the water, attach another anchor to the system, and then just continue that process back and forth. As far as the GPSing goes, we have a floating GPS that sits on top of the plow, floats on top of the water, and basically records the plowing location.